All right, guys, so we are almost to the end of Unit 9, which means we are almost to the end of AP Chemistry. Really, our final topic here is electrochemistry. So today we're going to focus on the electrochemical cell, both galvanic, meaning spontaneous, and electrolytic cells, which are non-spontaneous cells. So we'll talk about the way that they're constructed, the various parts, how they work, and how we can use them to harness the energy of chemistry to do work. So let's jump right in. Okay. So electrochemistry. So we're going to do a quick review of some terminology that should sound familiar to you. And I will also make a separate video for you reviewing oxidation states so that we can remember how to assign those. So when we talk about electrochemistry, we have two really important terms, and those are oxidation and reduction. And so when we talk about oxidation, we're talking about a process in which an element attains a more positive oxidation state. Or another way of putting that is that we are talking about a process where an element or a ion loses an electron. So we can remember losing electrons is oxidation. We also talk about reduction. And reduction is a process where the element attains a more negative oxidation state, or we talk about it gaining electrons. And so oxidation and reduction are always paired. You cannot have something gain an electron if you don't also have something else losing an electron. So oxidation and reduction always go together. We usually talk about reduction oxidation or redox processes. So here we have sodium losing an electron. We know that it's losing the electron because the electron is on the product side. It has left the sodium atom, and we now have a sodium ion and a free electron. Reduction is the process where chlorine gains electrons. So here we have diatomic chlorine gaining 2 electrons and becoming 2 individual chloride ions. Now, in order to put these together, we would have to have the process with sodium, the oxidation process, happen twice so that there would be 2 electrons available for the chlorine. So we have an element that is oxidized and an element that is reduced. We will also hear the terms oxidizing agent and reducing agent. When we talk about oxidizing agent, it is the thing that makes something else oxidize. It makes something else lose electrons, so it is reduced. Similarly, the reducing agent reduces something else, makes something else gain electrons, so it is oxidized. All right, a few more terms. Electrochemical cells are cells where electrons are transferred. We frequently use the term electrochemical cell to talk about a spontaneous cell, but an electrochemical cell in and of itself is not necessarily spontaneous. But if we talk about a voltaic cell or a galvanic cell, now it has to be spontaneous. Batteries are great examples of electrochemical cells. They are also frequently referred to as voltaic or galvanic cells. Now, an electrolytic cell is one where we have an outside source of energy that is used to cause a non-spontaneous reaction to happen. So we can think about things like recharging a battery or electroplating, and both of those are electrolytic cells. We use an outside electrical source to make the non-spontaneous reaction happen. Okay. So let's talk about our electrochemical cell and what it's made of. So our electrochemical cell is made of 2 half cells, and it's easy to picture these, and we will very frequently see this shortcut as 2 beakers, and each beaker contains a solution, and in that solution, usually you'll have a strip of metal. And so we have these labeled as metal 1 and metal 2. You can see that our solution is also made of ions of metal 1 and ions of metal 2. And notice that they are matched up. So you're going to have ions of metal 2 in the solution with the metal 2 electrode and ions of metal 1 in the solution with the metal 1 electrode. You'll also have some sort of an anion floating around in the water because we had to use an ionic compound to make the solution. So we'll use these terms anode and cathode. An electrode is simply the conducting part of the cell that is in contact with the solution. Usually a strip of metal, it can be a tube with a gas inside, but it is usually a strip of metal. It is the conducting part that is in contact with the solution. Now, when we talk about the anode, we are talking about the electrode where oxidation happens. So we can remember that it's an-ox. Anode is oxidation. And of course, we have a cathode, and the cathode is the electrode where reduction occurs. And so we can remember that we have a red cat, and reduction always happens at the cathode. So far we have our two half cells. Each half cell contains a solution and an electrode. Now those two cells have to be connected by this thing we call a salt bridge. Okay, so this is the salt bridge. It's usually either a strip of paper or a strip of fabric that is saturated with a solution of an ionic compound. And the salt bridge is here because as electrons flow, because once this cell is all connected, the electrons are actually going to flow from the anode to the cathode through a wire. Now, we know that as the electrons flow, that we're going to have negatively charged things being carried over towards this side. And as those negatively charged objects, those electrons, move over to this side, that would cause a buildup of negative charge on this side in this half cell. And so very quickly, the cell would stop working because the electrons are not going to continue to flow if there's a negative charge on this side, because like charges repel. And so we have this salt bridge, and inside our salt bridge, these ions are free to move between the two solutions. And so the positive ion is going to flow in the same direction as the electrons in order to balance that charge. And the negative ion is going to flow in the opposite direction also in order to balance the charge, because this side would be becoming more and more positive because it's losing electrons. So far we have our half cells with the solution, the electrode, connected by the salt bridge, and then they also need to be connected by something that can conduct electricity, something to conduct the electrons. And usually in the center, we're going to have a voltmeter, and that's going to measure the voltage that is flowing from the anode to the cathode. So how do we know that it's going to flow from the anode to the cathode? Well, at the anode, we know that oxidation is occurring. It's losing electrons. So what's happening over here is that our little strip of metal here is losing electrons. That means that it's forming the more of the metal ions, and those are dissolving in the solution. The electrons are flowing through the wire and over to this side where the electrons are being added to the ions in solution and making more of the solid metal. So that means that on this side, our metal is gaining mass and our solution is losing concentration. Whereas on the anode side, our metal is losing mass and the solution is gaining concentration. And we can remember that because not only is it a red cat, it is a fat red cat. And so the red cat, the cathode where reduction is occurring, gets fatter as our process goes on. Okay, anything else we've missed? Oh, we can see our direction of electron flow. And as I've said, they're going to flow from the anode to the cathode. And the negatively charged ions are going to flow the opposite direction in the salt bridge from the electrons. The positively charged ions are going to flow in the same direction as the electrons. So those are our half cells. If any of this connection stops, if the wire is removed, the cell stops working. If the salt bridge is removed, the cell stops working. If our solution over here runs out of ions, the cell stops working. If our anode over here is consumed, the cell stops working. So we have to have all of these pieces in order for our reaction to happen. In a voltaic cell, we take advantage of the fact that electrons flow when we connect them in this way, and we make them flow through an external device, and we can use those electrons to do work because the electron flow is what we call electricity. So you can see in this image that we have a copper half cell, and this is probably a zinc half cell, looking at that voltage. And instead of a salt bridge, here we have what's called a porous ceramic disc. And so the positively and negatively charged ions are able to flow back and forth between those two. So this is a voltaic cell or a battery. Just like water only flows one way in a waterfall, it's always going to flow down. It's never going to flow up. Electrons only flow spontaneously in one direction in a redox reaction. They're going to flow from the higher potential energy to the lower potential energy, just like the water falls from this area of high potential energy, because it's up high, to this area of low potential energy. And just as this potential energy is converted to kinetic energy, here we are converting potential energy to electrical energy. So we call the difference between the anode and the cathode the electromotive force. We also call it the cell potential. That's what we're going to call it for the most part in AP chemistry, and we designate it as E sub cell. That cell potential is measured in volts, and a volt is a joule per coulomb. So a coulomb is the charge on a mole of electrons, or the charge, charge per mole of electrons. Okay. In order to be able to figure out what this difference is, what this cell potential is, we have to have a way of measuring it. We can't measure cell potential directly. We have to have a reference point. And so we create a reference point, and that reference point is what we call the standard hydrogen electrode. And all electrodes, all half cells, are measured in comparison to the hydrogen potential, standard hydrogen electrode potential. So we set the standard hydrogen electrode potential as 0, and we measure everything else as a difference, voltage difference, when it is connected to that hydrogen electrode. And so what that allows us to do is to set up this table. And this table is all of our reduction potentials. These potentials are like our potential energy. So the higher the potential is, the higher its reduction potential is, the more likely it is to be reduced. The lower it is, the lower the reduction potential, which we could also think of as the higher oxidation potential, and the less likely it is to be reduced. So we'll use these to determine the cell potential, the difference between the potential of one electrode and the potential of the other electrode will tell us the potential of the cell. When we think about our galvanic cells, spontaneous redox processes, so a spontaneous reaction has a negative delta G. It will also have a positive cell potential. So when we talk about a galvanic cell, it's a spontaneous cell, and it will have a positive cell potential. And this will allow us to determine which one is going to be our anode and which one is going to be our cathode. So if we look at the zinc copper galvanic cell, we're going to look at our reduction potential table, and we're going to see that the reduction potential of the zinc electrode is negative 0.76. And the reduction potential of the copper is going to be 0.34 volts. So that means that the copper has the higher reduction potential. So the copper will be the cathode, the copper will be reduced, and the zinc will be oxidized. So our less positive reduction potential becomes our oxidation half reaction, and our more positive reduction potential stays the same. So you notice that we've flipped our equation here so that instead of writing both of them as reduction reactions, we're now writing copper as the reduction reaction and zinc as the oxidation reaction. So in this cell, we now know that the electrons are going to flow from the zinc to the copper. The concentration of the copper solution is going to decrease. The mass of the copper anode is going to increase. The concentration of the zinc solution is going to increase, and the mass of the zinc electrode is going to decrease. One more piece that we can determine from this information is what the cell potential is. So you notice that when we flipped the reaction, the zinc reaction, to become an oxidation reaction, we also flipped the sign on the cell, on the half cell potential. And so now we're going to add them up, and we can find that the cell potential for this cell is 1.10 volts. We have two different ways to think about standard cell potentials. You can look at it the way we just did and say that the cell potential is equal to the oxidation potential plus the reduction potential. This requires you to flip the sign on the reduction potential of the oxidation reaction. Or you can think of it that the cell potential is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. And when we do that, then the minus sign takes care of flipping the sign for you. And so in that case, we would have 0.34 minus negative 0.76, and we would still wind up with a cell potential of 1.10. If you're ever confused and you forget which one to put first, big minus small, if it's a spontaneous cell, this number has to be positive. And the only way it's going to be positive is if we have big minus small. And of course, because cell potential is based on the potential energy per unit of charge, it is an intensive property, not an extensive. So unlike the other units that we've been working with in this unit, you do not need to multiply this by the number of moles. Okay, so whether we're talking about copper, which transfers copper 2, which transfers 2 electrons, or silver, which only transfers 1, we don't need to multiply by a coefficient. Okay, we can, again, we're still in thermochemistry. We can also calculate the free energy of the cell from the cell potential. So the standard free energy is equal to negative N, where N is the number of moles of electrons, times F, where F is the Faraday constant, whoops, there it is, which is 96,485 coulombs per mole of electrons, times the cell potential in volts. So we have our cell potential here of 1.10 volts, and we can calculate delta G. We have 2 moles of electrons. We have 96,485 coulombs per mole of electrons. And we have 1.10 volts, but we also know that a volt is a joule per coulomb. So we can cancel out coulombs, we can cancel out moles of electrons, and we're left with a delta G in joules of negative 212,267, or we can say negative 212 kilojoules. So we can see that we have a positive cell potential and a negative delta G. And we would expect those two to go together because those two things have to be true in order to have a spontaneous reaction. Okay, that's spontaneous. Let's talk about non-spontaneous cells. These are electrolytic cells. So an electrolytic process is not a spontaneous process. They have a negative cell potential. They have a positive free energy change. These have to have an external power source. When we draw these cells, when we're looking at these cells, you must see this external power source, this external battery. Electrons are still going to flow from the anode to the cathode. We're still going to have oxidation happening at the anode and reduction happening at the cathode. The difference is that they are not spontaneously flowing this way. They are being forced to flow this way by this external power source. So a couple of examples of those. The electrolysis of water. This is one of the ways that we generate hydrogen gas and oxygen gas for industrial purposes. So by applying an electric current in an acidic solution, we can actually cause water to break apart into hydrogen ions and oxygen molecules and release 4 electrons. And we can also have water gaining 4 electrons, forming hydrogen gas and hydroxide ions. And so you can see that we have cathode and anode. Our cathode is negative 0.83 volts. Our anode reaction is negative 1.23 volts. And we have a total cell potential of negative 2.06 volts. So we have a negative cell potential. This is not a spontaneous reaction. Another common application of non-spontaneous cells is electroplating. So if we want to coat the surface of a metal with a more expensive metal, but not use the same expensive metal all the way through, then we can electroplate. This gives a very smooth, very even coating. And many people have this. We have silver plate. Maybe some of you have silver plate in your homes, where a less expensive metal is coated with silver. So electroplating, we have to have a anode made of the plating metal. We have to have a solution of that plating metal. And we have to have a cathode with the object that we want to plate onto as part of it. And then we, again, because this is a non-spontaneous cell, need to have that external source of current, or that external power source. So what's different in this cell is that the anode reaction and the cathode reaction are opposites of the same reaction. So at our anode, electrons are flowing from the anode to the cathode. And as part of that process, our silver bar is breaking up. We are getting silver ions and electrons. Those silver ions are going into solution. Over here at the cathode, where we're bringing the current in, the silver ions are reacting with the electrons and forming solid silver on the surface of the spoon. So a very practical application. And we will learn tomorrow how to calculate how much silver can actually be plated. We do have one more video today about non-standard cells, not non-spontaneous, but non-standard. But that's it for standard electrochemical cells. So as always, if you have any questions, let me know.